There, in the plane, you have an oscillation. The pointing vector is not that much interested in it.
Okay. Because it's important to get this clear, exactly what you mean by internal and what some us physicists would mean by internal.
Okay.
Good.
But my internal variable...
Yours is clear.
That's good. My internal variables make physicists' representations. The clue is, this is a geometric approach, giving the reason of C-star algebras. You can do it directly with C-star algebras and forget the vector field and say that's
no, this is interesting, this vector field idea. You essentially got a field of Penrose's flags.
Yeah.
This structure is just a Penrose flag.
It has very much to do with it. Yeah, that's true. The question is, can one do this on not on a 3 manifold, but also on a 4 manifold, say on a Minkowski manifold, and that one can, not in that simple form.
No, because here you're just using quaternions.
I use the quaternions, and I take then the unit sphere again, that's the SU2, and I can start almost in the same, almost verbatim. But I would hesitate to say this is a sort of a relativistic quantization, because I haven't. The relativistic geometry comes in clearly, but it does not. It's not clear to me what that term relativistic by the quantization means. So therefore, I stop here and don't go further into the rest. So I'm over.
Multiplication of the wire elements, and there is this e to the power of something, and that's a twist.
Yeah.
Because it, by associativity, it gives you a coscycle.
Yes.
If you write the associativity.
And that's all you mean.
That's all I mean. So that's a twisted version of a well, it's a coscycle twist of a Hopf algebra, which is by this group algebra.
Actually, that's
and then you get projective representation because it's a twisted group.
Yes, and then you have to go and lift them up.
Like multipliers.
Like in the case of metaplectic representations in ordinary quantum mechanics. Exactly in the same way. Yeah, that's true.
Okay.
It's links up directly. Now look at the sphere. At the sphere you have the upper cap and the lower cap, if you have north and south pole. And you have an intersection. And on the upper cap the bundle is trivial, and the lower cap the bundle is trivial. But in the common zone, the bundles are not rightly connected. Looking at the type of bundle you have, you need to rotate the bundle a bit. And this rotation is the co-cycle of the Chern class. And that is built up with EI to Cn. So the Chern class is there. And then that's your winding number. That winding number pulls directly back to, since I work with these pullbacks constructions, to the manifold. But of course, the quality of the vector field enters by the quality of this epsilon, this unit vector field. And there is the mapping degree. And that mapping degree dictates the particular n you have to work with for the particular field. Every field has its own n. So associated with a field,
each field has its own n.
Yes, the mapping degree. And the Chern class is determined by the mapping degree.
Just wondering what that would be in physics. Okay.
Oh, it means the following. So first, remember, the vector field is quantized, and you have, nice space, presupposed then this mapping degree, which is an integer. So every vector field comes naturally with the integer. Now, where does this play a role in physics? Suppose my M splits into these two parts, coming from upper cap, pullback of upper cap, and pullback of lower cap. We have a common zone. Of course, each part, upper cap, since it is the preimage of an open set, is open, therefore the three-manifold, and I can do the construction here. I did exactly on this side. But the question is, do two representations I took fit together to one representation for the total space? And for that matter, the two representations have to match to that mapping degree. So that's how the topology enters intrinsic quantization. So it's, to answer the question, I'm wondering what it means, the topological grounds tell you how to manage.
Still doesn't really answer the question of the physical, but I see the mathematical structure.
Yeah, well, if every representation obtuses, so you don't have to from the global thing to the local thing, and you don't worry, of course, if you work locally.
Yeah, okay.
With quantum field theories. But the question is, if you have quantized locally in charts, as physicists do they match up? And how would one have to construct a match-up? There is a match-up, and it is determined by the mapping degree. So I think...
but how could then this binding number be different? I mean, what causes the difference then, in physics?
Yeah, the difference is given by the quality of the map. Now, if you have an oriented, look, first of all, the three-manifold is mapped to a part on a two-dimensional sphere. So here you have three dimensions, so you have one dimension. And most likely this map is not injective. You lose them, it would be a homeomorphism if you would have the same dimension. So there is a vibration associated to the map. The fiber is just a preimage of a point. Now think it is very nice. Think it is discrete. But the whole story works not discrete. Look what happens to the orientation. The map carries the orientation with it, but it can reverse it or not. Now there is a very strange thing, namely the mapping degree, which is a topological invariant, which counts the reverses versus the plus, say, it keeps the orientation. It says how wild that map is. And this wildness, that causes the mapping degree. If you could do it with the winding number, with associating a winding number, or there is in algebraic topology the intersection theory, intersecting one manifold with another, that is then the generalization of this winding number business, of this changing orientation.